Let's talk about a beautiful 10-page paper of Professor Wenger from 2008, Characterization of Metric Trees and Gromov Hyperbolic Spaces. The main statement of the paper generalizes a result that was almost at the same time proved by different methods by some other authors. And that result is that a geodesic metric space is a metric tree if and only if the intersection of any two closed balls is either empty, trivial, or again is a ball. We see that in plane that is not the case. If you intersect two balls, this set here is not realized as a ball of some center and some radius. It's never equal to that in the generic setting. So this strong result claims that this property characterizes metric trees. Only metric trees have this property. Let me quickly recall what a metric tree is. First of all, it's a geodesic metric space, which is quite a strong assumption to begin with, because first of all, we claim that every 2 points can be connected by a rectifiable path, and that the length of that path is exactly equal to the distance. So there exists some rectifiable path from 0 and the number distance of x to y, which is non-zero, into your metric space, such that gamma of t, distance from gamma of s, is precisely s minus t. So this path is parameterized by arc length. The definition is that all the geodesic triangles are tripods. That means the three geodesics could be in this form, and without loss of generality, let's say we label this x, y, and z. Or the path from x to z is like that. The path from x to y is like that, and then the geodesic from y to z is like that. So such an object is called a tripod. This also technically we can call a tripod, and therefore by definition, as one of the definitions used here, is that all the geodesic triangles are basically tripods. So now we can read the corollary again. A metric space, a geodesic metric space, is a tree if and only if the intersection of any two closed balls is again a ball, if it's not empty. And again, this result was proved also by these other authors. What the main theorem of this paper by Professor Wenger is that an apparently weaker condition already implies that the space is a metric tree. And that apparently weaker condition is that there exists a universal lambda such that the intersection of any two balls, when they are non-empty, contains a ball of radius nu and is contained in a ball of radius lambda nu. The centers, notice, do not have to be equal in this case. It's saying that the ratio between the largest ball inside this intersection and the radius of the smallest ball that contains that intersection grows linearly. So this lambda is the universal factor that works out. Again, want to go back to case of R2. Let's see why R2 is not a tree. Why doesn't it satisfy this condition? If you take balls of radius r and then align them so that there is this h much intersection here, so the smallest ball, the largest ball you can fit in there, let's say has radius h, then the ball that contains them, this radius will be of order root of h, not a constant multiple of h. So therefore such lambda does not exist that would work in all scales and all orientations of the balls. Posteriori, we will know that actually you can take z equal to z bar and lambda just equal to 1. Therefore, this intersection is indeed actually just one ball. And the proof of it, very different from this paper, is very analytic. So it depends on integrating stuff and taking derivative of Lipschitz maps basically from R2 into metric spaces in the sense of Kirchheim. It's again, the whole paper is 10 pages including references and everything, and it's very well written, so all details can be found there. Also, as a byproduct of reading through this paper, I learned something very basic about triangles that I hadn't seen before ever. Although I spent a good deal of time in my high school years working through these all triangle equation stuff, I had never seen this before and it was quite curious to me. I wanted to share that with you. What we are saying works in the generality of geodesic metric spaces. So my triangle is really just a geodesic triangle in any metric space. Proof would go the same way, except that we have to remember that this triangle is not necessarily embedded in R2. But for simplicity, let's say we are looking at some generic triangle in R2 with the vertices x1, x2, x3. The claim is that there exist numbers a1 positive, a2 positive, and a3 positive. So basically one number for each vertex, such that it says that if you travel a1 much along from x1, so a1 travel this much, so in the metric again setting, this would be that you go for a1 time along the arc length parameterized geodesic. So you go a1 from x1, you travel a2 from x2 toward each of the other indices, other vertices, and then you travel a3 much from x3, and then this would perfectly line up. So that means they will meet right in the middle, so there will be no overlap and there will be no gap. So in other words, distance of x1 and xi and xj basically would be just ai plus aj for all I in 1, 2, 3 and j in 1, 2, 3, but not I itself. Okay, I go t much from x1 towards each of the indices, and then this here will be d12. Let me just for short say d of xi xj is dij, just for short notation. Minus t is this much left, and here d13 minus t is left. And and then I look how much I will have here. So if I run the same, so these are my candidates for a1, a2, a3, except that they don't satisfy the property I want. Because if I travel d12 minus t here, and then I travel d13 minus t here, I don't know if they match exactly where I want them to match. There could be overlap, they add to too much, or there would be a gap so they don't add up to distance of x2 and x3. Length covered on x2, x3 edge will then be x1, x2 minus t plus d of x1, x3 minus t. So this is actually a linear equation. So if is linear and hence continuous. And now I see what happens at the extreme ends. So f of 0 will be d of x1 plus x2, x1, x2 plus d of x1, x3. But by triangle inequality, which also holds in metric space, is bigger than distance of x2 to x3. Let's say without loss of generality, assume d of x1, x2 is smaller between dx1, 2 and dx1, 3. So I have two edges from x1, and I assume that the x1, x2 is the smaller one. By symmetry, it wouldn't matter. And now the maximum t that makes sense that I can make is take all of d1, d2. So you now go all the way extreme to this end, and nothing is left back to this guy. But then we see that, by the way, also this is strict because we don't have degenerate triangle, let's say. And this case, my f formula, so one of them will be 0 here, this one, and I will be left with d of x1 and x3 minus d of x1 and x2. But then again, by triangle inequality, we can see that this is strictly less than d of x2 and x3. Because if you put this on this other side, x2 is common to them. So by triangle inequality, you get a bound on x1, x3. Okay, so you have a continuous function on the interval, say 0 to dx1, dx2. At the beginning, it's strictly bigger than some value, and then at the end of the other end of the interval, it's strictly less than that. So somewhere by intermediate value theorem, I may have said mean value theorem because I love that theorem a lot, and I always confuse this intermediate value theorem. I misspeak and say mean value theorem. Intermediate value theorem then implies there exists something in between that interval. Because these inequalities are strict, it doesn't happen at the intervals. So that means there is some t strictly positive and also strictly less than d of x1, x2, such that and this will imply that all the a2 and a3s are also good, such that f of t is equal to dx2 and x3. And if you chase this definition of ft, it then shows that setting a1 equal to t, a2 equal to d of x1, x2 minus t, and a3 equal to d of x1, x3 minus t satisfy the claims. Okay, let me know in the comments if you find this at all interesting, or is it just me, and whether you had seen this before, or does it really come that naturally to you. To me, the fact that given any triangle there are these numbers a1, a2, and a3 which perfectly match up like this is kind of surprising.